be greater than 1. In other words, if you draw a number line, probability can be 0, probability can be 1, but probability of any event is not allowed to be greater than 1. Also, probability of any event, probability of event X is not allowed to be less than 0. Another way of saying that you cannot get a negative probability. If you do, it's a mathematical fallacy. Also, you cannot get a positive, a number greater than 1. So suppose you finish solving a probability problem and you have 1.2. That probability is wrong, can never be. It's a mathematical fallacy. So probability has to range from 0 to 1. The sum of all the probabilities must be 1. So there are the sum sigma of all the probabilities of X must be equal to 1. That is why we say that area under the normal curve is 1. The total probability is 1. All right, so we're not going to talk about so many things. We're just going to talk about important things. So probability model, what I'm going to do from now, since that we have defined the probability, what I want to quickly do now is go to practice tests, and so we can see some examples and talk about some examples of probability and see how we can answer the questions. All right, so I'm going to come to that practice test, and then we can use that to answer some questions. All right, so I'm going to clean a little bit of that. All right, so I come back to cleaning. Cleaning doesn't work with this. It doesn't really try to clean well. Okay, so I can, let me see what else can I do with cleaning this. Okay, I'll go and do something else I used to do, get my whiteboard. So I get a whiteboard and see how that one goes. All right, so we let's get to whiteboard, and I'm going to clean the whiteboard. Hopefully the whiteboard is going to work today. So we defined probability already. The probabilities, properties of probability. So let me say probability of event A. So we already said property number 1 is that 0 is less than or equal to probability of any event is less than or equal to 1. There are 2 important probabilities. You cannot miss it because we carry it from now to unit 4. So summation of all the probabilities of event E is equal to 1, can never be more than 1. So that is what this table is showing us. That's what the table is trying to show. But so the table is trying to show that if I add all the probabilities, I must get 1. If the probability, if the sum is not equal to 1, then I'm going to 5 though. If the sum of all the probabilities is not 1, then it is not a probability distribution. Okay, so let's look at this, and maybe we need to, if this is from one bag, if this is from one bag and I add all the probabilities and the sum of all the probabilities of the colors is not equal to 1, then it is not a probability distribution. So I just take this, that this is a probability distribution until I add them up and they are not equal to 1. That is the meaning of the sum of all the probabilities must be 1. It doesn't matter if it is the sum of qualitative variable. This is qualitative because brown, yellow, orange addition may not make sense, but still. Okay, so if I add all this up, okay, let me get a calculator so I can. This is a probability model. We must show that rules 1 and 2 exist. So rule 1 says that there should be no negative probability. So there is no negative probability. If I'm told to test the rules of probability, I will test this table and say there is no negative probability. Therefore, rule 1 is correct. Then let me test rule 2. Rule number 2. Rule number 2. So rule number 2, I want to add all the probabilities. 0.13 plus 0.14 plus 0.13 plus 0.24 plus 0.2 plus 0.16. All right, if I did the addition correctly, if I add them up, the answer must be 1. If the answer is not 1, then the distribution is not a probability distribution. So this is the first thing we need to cover today. Knowing there are 2 laws of probability and knowing how to apply them. So we learned that the probability of an event is between 0 and 1. In other words, probability can be anything between 0 and 1. The probability of event can be 0.3, 0.1, 0.999, but it cannot be more than 1. If the probability is 1, we'd say that the event is certainty. It's a certainty. It must happen. If the probability is 0, we say that the event, the probability of the event happening is 0. It cannot happen. It's impossible, uncertain. So, so this describes, explains the laws of probability, and that is the first section, section 5.1. There are so many things in section 5.1. We're not interested in them because there's a lot of things we have in the book, but we are following what is in the syllabus. So in our syllabus, well, the only thing we need to know is probability rule and apply it. So we have known the probability rule is between 0 and 1, and if I'm given a table, I should be able to say if the table is a probability distribution or not. If none of the probabilities is negative, and if the sum of all the probabilities is 1, so we know, hopefully we know 5.1, the first one. Addition rule. So we're going to the next thing we need to know. So what in the world is addition rule? So number 2 or for 5.2, and I want you to know that 5.2 contains more things, but I'm not required to be reading every PowerPoint. There are some that the students can read. The most important thing in 5.2 says that there are 2 kinds, let me say addition rule. Let me just addition rule. Addition rule. So there are 2 kinds of addition rule. Rule number 1. Addition rule number 1. Addition rule number 1 says that 2 events, event A and event B are mutually exclusive, exclusive if the probability of A union B, I can write it this way. If the probability of A union B is equal to probability of A plus probability of B only. If the events are mutually exclusive, they cannot intersect. So actually, I will use what is called a Venn diagram to explain addition rule. So I'm going to draw a Venn diagram. I can draw that Venn diagram here. So a Venn diagram, we remember when we were doing, if I draw a Venn diagram, this is a universal set. So suppose this is A and this is B. If they cannot touch each other, they are mutually exclusive. They are mutually exclusive. If they cannot touch each other, nothing connects them, they are mutually exclusive. There are so many events that are mutually exclusive, but we're going to use human beings. Suppose somebody in class today, okay, say Terry and Roxana are here. There is no possibility that we can also be teaching another class right now. The probability that Terry and Roxana or any of us is teaching another class when we are already teaching this class at this moment are not connected. They cannot happen. It's impossible. So they are mutually exclusive. We can only be teaching one class at a time. If we are supposed to be teaching one class at a time, then we are teaching one class at a time. So I'm going to use just myself. So there are things in the real world that are mutually exclusive. A whole lot of things. If a car, the model of a car is done, a car is done by Toyota, the same car cannot be done by what's the name of the other? What's the name? There are so many of them. Ford. So it's either made by Toyota or made by Ford. It cannot be both Ford. A car cannot be made by Ford and Camry at a time, or Toyota at a time. So the make of a car are mutually exclusive. There's no way you can ever go to school and say, okay, I have to register my car. My car is made of Ford and Toyota. No, they will be looking at you as if you're mad. So that should be mutually exclusive. So statistically, in probability, if two events are mutually exclusive, they cannot happen at the same time. And one of the probability rules called addition rule says they are mutually exclusive. And another name is disjoint. If two events are mutually exclusive, they are disjoint. Another name for mutually exclusive. So this is rule number one. There is no intersection. Even if somebody creates an intersection, I'm going to get this off. Even if somebody creates an intersection, the intersection, okay, let me see if I can get this off or move it out. Okay. All right. Suppose I have, all right. All right. So if two events are mutually exclusive, probability of A union means O, by the way. Union B, I can say O here, is equal to probability of A. I already wrote it before, plus probability of B. Even if somebody says minus the intersection, probability of B, A intersection B, then this intersection has to be 0. The intersection in mutually exclusive events is 0 because they don't intersect. 0, the intersection is 0. And by the way, intersection is and is intersection. All right, so now addition rule number 2. When we answer this addition rule, when we finish addition rule, we go to a practice test and try to do some problems on addition rule. Addition rule number 2. There are 2 addition rules. Addition rule number 2. Let's call it joint events. If 2 events are joint or non-mutually exclusive, non-mutually exclusive, then we can say that 2 events obey addition rule number 2. So let's go ahead and draw a Venn diagram like you did. If 2 events are non-mutually exclusive, forgive my crooked Venn diagram. So this is A and B. All right. Suppose we are talking about A. If event A is maybe students in this class taking biology. I read their discussion. So most students are taking statistics and biology. So if the student is a girl, it can be a girl and be taking biology. If the student is a boy, it can be a boy and taking biology. Therefore, being a girl and taking biology and being a boy and taking biology, they are not mutually exclusive. You cannot say you are a girl and you can't take biology at the same time. You cannot say a boy, you cannot take biology at the same time. So these are non-mutually exclusive. And we can already see their intersection. We can already see their intersection. So there's an intersection between them. So these 2 are I'm going to start here, non-mutually exclusive. Non-mutually exclusive. Because their Venn diagrams is intersection. So non-mutually exclusive are called joint events, and they are also called probability rule number 2. How can I demonstrate that using my, okay, I can demonstrate that using my, all right. So let's use equation or probability equation. So I can say a probability of A union B in a non-mutually exclusive event is equal to probability of A plus probability of B minus probability of A and B, and its intersection. Like I said before, anytime you see union, it is or, and or always means addition, and means multiplication. When we are coming to that, and means multiplication. So we have drawn a diagram to show non-mutually exclusive events. We have just given an example, or let's call it a Venn diagram and equation So let's do example. Until we do an example, we will not know how to. So we did probability rules, and we used the table to show example. So let me see if there's a quick example in chapter 5. But where I'm going to go anyway, I'm going to see if there's a Venn diagram quickly. Let me see if there's a Venn diagram we can use. If not, I'll use my own Venn diagram. It's important that every student reads this. That's a lot to read here, but we really don't have all this time to cover all this. We have, yes, okay. So I see a Venn diagram. And the Venn diagram, okay. So the Venn diagram is actually in PowerPoint number 45. So you can see that this is for mutually exclusive events. They don't meet. And then if I'm not going to start, we haven't done calculation. So we're going to do calculation very soon. All right, so this is an example I just gave. An event, or if two events are disjoint, this is the formula. I just wrote that. And by the way, you can use any letters. You can use any letters in your, there could be three of them. There could be three of them. Three can be disjoints. All right, so the law of the addition rule, that's what they are writing here. But we really need to use an example. Let me see, that's another Venn diagram. Because, okay, yeah. Now, I just explained another probability. The important thing, there are two of them. The important things, there could be disjoint or joint. So this is an example of joint. And this is the formula for joint. So I just want you to know that the formula for joint, you don't have to know the formula sometimes. Maybe if you know that if they have an intersection, then they are joint, and they are not mutually exclusive events. And then that's called the probability rule 2. And by the way, you can call any of them 1 and 2. There is something in the joint. There's something in the joint. And that shows, that is the reason why you said that they are non-mutually exclusive, because there's something between them. Okay, let me see. Okay, so I have seen the diagrams that I need. So now let's go get some examples from a, if we can solve some examples from a practice test. Okay, try, I didn't clean this before. Let me see again if I can clean. There's anything that can clean it, and then we can see. Let me see. I know why. Okay. Whatever I can clean, that's fine for me. All right, so we want to do examples of 5.2. The most important thing we need to know from 5.2, so that we can go to 5.3. Because within a short time, we have to cover 7 sections. So this section, this unit 2 is very fast. Unit 2 is very fast. We need to, okay, this is good enough. All right, so let's see an example of probability rules when they are actually disjoint. Okay, if E and F are not disjoint, so everybody look, this, sometimes they ask a question that looks like it's a tautology. All right, so this and that are not disjoint. I'm going to put it down. All right, so they're telling us that E and F are not disjoint. If they are not disjoint, then they are joint. Not disjoint means they are joint. Okay, I hope you understand. If E and F, these are events. If event E and event F are not disjoint events, then P is asking you to answer the question though. It's asking us, now that we have done it. Then what is the probability of E or F? In other words, what is the probability of event E union F happening at the same time? Remember, the question told you already that they are not disjoint. So they are joint. So you will, if you can, explain the probability with your diagram. It's always good to explain the probability with a diagram if you can. You draw a Venn diagram. A picture tells 1,000 words, even more than 1,000 words. So I'll call this one E, and I'll call this one F. All right. And this disjoint shows point of intersection. Okay. By the way, I am told that they are joint because I see this is what I say tautology, because they could have asked us if A, E, and F are joint. Why are they saying not disjoint? That is, so you can rewrite the question by yourself. If E and F are joint, that's better for me. All right, no problem. You can figure that out. So I can write the formula for myself. Probability rule, I can call this probability rule number 2, says if E and F union, probability of E union F is equal to probability, come on, get out, probability of E plus probability of F. Then you have to put the intersection. This is F here. Can you get out of? All right, I got to write it again. Okay, I'm going to write it again. Just making some. Okay. So probability of E or F. Remember, I can use union for or. So that is probability of E plus probability of F minus probability of E union F. I mean, E intersection F, that intersection. Remember, we drew a Venn diagram, and a Venn diagram looked like this. A Venn diagram looked like that. Draw. So your Venn diagram has to show their intersection. Just no, anyway, I just try and minimize this and see if it's going to be better, because this board actually don't want me to write. Okay, so anyway, I'm going to check this answer now and find out which one is this. Which of my answers says P intersect P union union F is equal to PE plus PF, probability of F, minus, give me time to take this one out also. All right, minus probability of A intersection F. E intersection F, remember it is and here. Okay, and then the formula, they will write the things there to confuse you. If you have paid attention so far, you will notice that the formula they are asking you, it is, first of all, let's eliminate. It is not this one, not this one, because we are not adding the intersection. We are not adding it. It is not this one because we are not subtracting the intersection. This is a probability rule number 1 for mutually exclusive. Therefore, this is the correct answer. Oh, but I know that this question is always in the test. This question is always in the test. So, okay, so let's get another. This question number 2 is Z-score. So whenever you see a Z-score question, you know we have already done it. Trust me, we have done Z-score, but question is going to always show up. It's always going to show up in the test. Z-score, we did it in 1.1. I mean, unit 1, but it's going to show up in the test, in every test. Okay. By the way, let's answer question number 3. It is still probability. And before we continue, I want us to say what is complement. So complement rule. So at this point, we need to know what complement rule is. Example, suppose I have this oval. Get my whiteboard because it behaves better. My whiteboard behaves better when I write on it. So suppose I have an oval that represents A. So if I have an oval, and this oval, A, contains numbers 1, 2, 3, 4, and there's another oval, B, that contains numbers 6, 7, 1, 5. Okay. A question can ask me, find find A union B complement C. Okay, so no problem. I'll find A union B. So if I find everything in A and B, the complements are things that are not in A and B. And I haven't even defined the universal set. So if I don't define universal set, you will not know what to say. So I am going to first of all define a universal set. Suppose I say that the universal set is another one, E, such that it starts from, it's a set. So it's a set, I'm using set notation. So I'm going to say that it is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, just let me stop at 9. So if I'm trying to find in A union B, so I just find A union B here. A union B will be everything in A and everything in B. Everything in A and everything in B. So if I get A union B will be everything in A and everything in B. Okay, remember this is the universal. This one defined it all. So I can start 1, 2, 3, 4. They are in A and B. 1, 2, 3, 4, 5, 6. I just have to do one time. And then 5, 6, 7. 5, 6, 7. And this is A union B. This is A union B. All right. Now, if I am told to find complement, but they are in the same union, it will be everything that is not here, but is in the universal set. So A union B complement, A union B complement will be everything that is not in A union B, but it's in the universal set. So is there anything in the universal set that is not in A union B? Yes, there are 8 and 9, the complement. Okay, so let's go to answer the questions on the board. Questions on the, we're going to be using set anyway. Some people don't like set, but it's not bad. So we're going to be using set notation to define. Remember, we started with a Venn diagram. In Venn diagrams, you use set. So question number 3. So we are given that S is a probability experiment is conducted in which the sample space, whenever you hear sample space in this class, in this unit 2, it means population. Okay? Sample space is population in probability. What is the sample space? What is the population? So, another way of saying universal set. Therefore, universal set is S. Okay. Okay, then they defined an event E. So let's see if there's any other thing. Assume each outcome is equally likely. Equally likely means everybody has equal opportunity to be selected. Equally likely, in other words, selection of 1 is as good as selection of 2. The probability of selecting a 1, let's count it. How many do we have in the universal set? 1, 2, 3, 4, 5, 6. So there are 12 of them. So the probability of selecting a 3 is 1 out of 12. Probability of selecting a 4 is 1 out of 12. Okay, so selecting any of them is equally likely. Outcome is equally likely. Okay, now question says find E complement. Very easy. It means find everything that is in the universal set, but they are not in E. Find E complement. E exponent C. I want you to know that some books, just in case you open your test and see E prime implies E complement. But sometimes the book says E prime. When you see E prime, it means E complement. E prime and E complement are the same. Okay, just make sure we said that and we can't forget that. Okay. So now I am going to pull up my whiteboard, sorry. My whiteboard. I put it down, bring up whiteboard, come up here. And then I am going to clean some stuff here out of there. And then let's answer the question, but you don't even need any, it's an easy question, but I want to make sure I answer it on a clean board. The other board is not really clean because sometimes it won't let me clean it. All right, so I'm getting this out, and then I'll answer question. What am I doing now? We talked about complement. We want to do an example. We talked about probability rule. We did an example. We talked about addition rule. There are 2 of them. You must know the 2 addition rules. What are they? One is mutually exclusive. You need to know the diagram. You need to know how to explain it with Venn diagram. You need to know how to explain it with equation. You need to identify a question that is mutually exclusive. And you need to be able to identify a question that is non-mutually exclusive. Okay, and you notice that we are summarizing, we have already summarized section 5.1, 5.2, and 5.3 right now, because that's the only way we can do all this within two classes. All right, so I am trying to take away. So now I get my pen. I get my pen and take away everything that is in. So note these things are in my event E, and I'm told to find E complement. So what I'm going to do is go here. I cancel whatever 5 is in E. I'll cancel 5 here. You can do it any other way. I like slashing it out. 6, cancel 6. 7 is here. When I finish, the ones that are not slashed out belong to the E complement. So, okay, I took 8 out here. 9, I'll take 9. 10, 10 is here. I'll take 10 out here, take 10 out there. I'm doing it like those in elementary school, but that's okay. Whatever you can do to make sure you conquer a problem. So what is the E complement? E complement are those not in E, all those ones that are not in E, and they are 3, 4, 13, 14. It's very easy. So they told us to write numbers that are not in E. That's all. What are those numbers that are not in E? Guess what? This is another question in the test. Okay. All right. We don't have all the time in the world, but there is something I want to start, because whatever we do is, so we just answered questions on probability rule, complement rule. We already know z-score, and then we know the rule number 1, rule number 2, and complement rule. And by the way, addition. Suppose I say PA, suppose of A. What is wrong with you? Okay. Suppose I say find the probability of A. This time I'm saying and probability of B, where probability of A is 0.1, probability of B is equal to 0.5. All the time, just know that whenever you have intersection, an intersection means and. Intersection means and. Therefore, probability of A intersection probability of B is 0.01 multiplied by 0.5. And you don't even have to use your calculator. When you multiply the two, you will notice that you have 0.0. We can still use calculator that way, because you want to make sure that your decimal points are good. Okay, so I'm multiplying, and for the benefit of the doubt, I'm using my calculator so that you cannot misplace your decimal point. So multiply by 0.5. Whenever you're doing multiplication, you want to know that if you get any answer greater than 1, it's a mathematical fallacy. Not allowed to have any answer greater than 1. If your answer is less than 1, it's a mathematical fallacy. You're not allowed to have an answer less than 1. Okay. Now, we want to do a number, maybe not in order. We're not going to be doing everything in order. So we want to do what is called counting principles. And counting principles is 5 point something, but we need to do that. We need to knock it out so we don't have to worry about. And by the way, it's calculations. So I like to do calculations first,